I'm here. Hello, everybody. I'm doing a mic check real quick first. I'm on my phone listening to the stream, and I want to see if. Okay, so I listened back to the previous stream, and it sounds like I'm just like yelling all the time. I don't want that to happen again, so I turned down the gain. So yeah, I just listened to that. The noise filter is doing pretty well. What if I changed it's a high CPU usage though. So what if I changed it to the low CPU quality suppressor? I also turned the latency to high again. I'm testing the lower quality filter. I think I like this amount of gain because I can hear myself well. But it's not like overpowering anything. It's not like I'm yelling. Clapping my hands. Rubbing the mic. Okay. The vine move didn't play. The latency is like almost a minute, honestly. It's like 30 seconds latency. That sucks. Welcome to the stream, Straight Jacket. I just was taking a look at the project I'm getting myself into. Oh, no wonder the vine move didn't play. Oh, the vine move did actually play. Like right after I said it didn't. But no wonder it didn't play also because the redeems are not actually I can't speak over myself. Hold on. Let me go back to my actual headphones. It is time to fluid up indeed. Okay. I'm back on my headphones. So it turns out the redeems source isn't actually on the starting soon, the pre-stream scene. Ah, heck yeah. We also have a new playlist, a lower energy playlist, where the songs are like a different vibe, called After Hours. Is Gravity going to be included? No, that's negligible. Gravity is not going to be included in the simulation, because that's like a negligible force. I'll have chat open on my phone, as always. My microphone is holding up pretty well. It's not like unplugging itself or anything, even though the wire's broken. I have this Godot project open. That's the software I use. Godot is how I code. We're doing it in 2D at first, and then we'll graduate to 3D once if it's necessary, honestly. It might just not be necessary. So, I don't like working in 3D. It's complicated and hurts my brain. Hurts my little brain. So I just looked into the I was just looking into the project I'm getting myself into. And it's gonna be a little bit of something. Hold on, let me. Yeah, this is what I'm getting myself into. I'm getting myself into all this stuff. The Euler equations. Each cell records its state, and this is the states. These must be conserved. We're doing a Euler fluid simulation because it seems like it's the best application for what I'm trying for. And we've got resources for learning fluid dynamics. Who's texting me? And we've got more equations, which these ones we shouldn't actually need. But it's like some actual like calculus. It's some actual like, oh, my roommate is asking me what my Chinese roommate is asking me why 9 plus 10 is 20 equals 21 is funny. Hold on, I gotta send that. I gotta send this to him. Oh, nice. If you understand some things, that's pretty nice. We're starting somewhere at least. I sort of understand, but I'm supposed to be an engineer. That's gonna be my major. So if I learn this, I've got some stuff on my side. I've got some like things to put on my resume once I get into engineering school. What's 9 plus 10 original video? Okay, hold on. I gotta go back to my channel and then go back to chat. Okay, is the music loud enough? Is the music a reasonable volume? I think I'm gonna turn it up a little bit, honestly. Yeah, I was looking back at the previous thing. It sounded like I was yelling all the time and the music was really quiet. So I turned down the gain. Sounds pretty good to me. And I just turned up the music. So we're gonna be watching some videos first, I think, and then we're gonna be compiling. Yeah. So we're first things we're gonna do is we're gonna create a new text file, and it's gonna be notes.txt. And let's edit this. So fluid simulation notes. So what we're gonna do is we're going to watch some YouTube videos, and we're gonna take notes on what's going on in them. We're gonna you know, digest all this stuff, and then we're gonna put it down in these notes, and then we're going to from that we're gonna look at real-time Eulerian fluid simulation. We're gonna look at Anj the Great, who is my main inspiration for this project because of his real-time trumpet simulation. Initial audio testing, engine simulator devlogs. Engine simulator is what because he's doing fluid simulations, the same thing as I am. And this is also a video I saw at some point where I don't. Ooh, check that out. That's a cool video. Maybe we should watch that too. Finland noise, rendering millions of particles. There's a lot of cool stuff we can watch here. But for now, let's just stick with. Maybe I'll put it in my watch later. Yeah, I already watched that, but you know. How do fluid simulations work? That's actually one that I want to open in a new tab. Exactly! X-brains think better than one. Okay, first of all, I'm liking this video. Okay, so we're gonna digest what's in this video. Let me get to my point. I keep getting distracted. We're gonna digest what's in the videos, and then we're going to put them in the Notes app, and then we're going to try some things. We're gonna try it until either it works or we get stuck hopelessly, and then we're gonna go research other things. I've also got the exercise sheets too. Lectures on fluid dynamics, numerical fluid mechanics. We've got all sorts of stuff here, and we're gonna figure it all out. Okay, I think we'll start with this video. Actually, you know what? We're gonna start with the trumpet video.
Hey, what's up guys, and welcome back. In today's video, we're going to be building Engine Simulator's fluid simulation and visualization system, and then using the system to simulate a trumpet. Before we get started, I'd like to thank BeamNG, Reina, Meister, Gold. I simulated a steam whistle using Engine Simulator's fluid simulation. To keep things simple, I'm going to refer to this fluid simulation as the legacy model. Some people pointed out that real steam whistles don't have springs or pistons or any other mechanical elements to achieve resonance, and this is true, and I'm aware of that. These
I don't know any of the mathematical equations of why fluids work. I understand it more from a natural sense. Of course. We're going to be learning this stuff together.
Virtual elements are
you're in the same boat as me.
The legacy fluid model is too coarse to model the complex acoustic phenomena inside the steam whistle. We're going to revisit this problem today, but this time with a slightly different musical instrument, the trumpet. The most challenging aspect of Engine Simulator is the requirement that it runs at or near real time, which seems to rule out a lot of the more advanced fluid simulation techniques.
This is one of the things that I'm really like thinking and worrying about, is that I have to run this. You have to run the simulation at 440,000 kilohertz in order to make reasonable audio. And another thing I'm worried about also is, how do you save that audio to a file on Godot? Like, how do you make a WAV file? Or a WAV file? Microsoft WAV file? We'll figure it all out. We'll figure it all out.
In fact, just running in real time isn't even enough, because we need to also generate real-time audio, which is usually sampled at 44 kilohertz or higher. That means we need to run the fluid simulation at least 44 kilohertz, or we'll start sacrificing audio quality. Most physics engines in games run at the game's frame rate or a little bit higher, so 60 to 200 Hz. Some games with more sophisticated simulations like BeamNG can run at around 2 kHz. The core idea behind the legacy fluid model is to simplify complex 3D elements into control volumes or cells. An intake runner, for example, is modeled as a rectangular prism with uniform temperature, pressure, and velocity inside. This is obviously a massive simplification, and a lot of the complex fluid
I know how to convert
the volume
them.
is lost.
But now the problem is that I have to sample arbitrary like pressure data and stuff. I have to sample that into a file. I'm not converting files here. I'm creating them is the problem. And I don't know how to do that. So I have to research all these like things like file structure and multi-threading and all that kind of stuff. We'll figure it all
out. I can
out.
still make some basic predictions about airflow. Most real fluid simulations subdivide the simulation domain into multiple control volumes, and the more control volumes you have, the more accurate the fluid
I feel like we're gonna have
simulation will
Audacity
be,
open
at
a
the cost
lot.
of being a lot more performance intensive. Considering that Engine Simulator
And foobar.
already uses the smallest possible resolution of basically 1.
Oh yeah, foobar. I should pin that to my taskbar. Foobar 2000. This is my audio. Let me set up the things on this right now, actually. Window capture, Audacity. That is foobar. There we go. Transform, fit to screen, and put that below Firefox. And then I want foobar as well. Okay. Yep. Same executable. Transform. Fit to screen. So the cool thing about foobar is that it actually has a spectrogram feature. So right here is the spectrogram.
Finland!
You see here, I can't zoom in any further or do any things, but that is the spectrogram. This is the graph of pitches that is in that Finland. Finland! A rising pitch and then falling pitch. This is the fundamental tone, and these are overtones, by the way. And the overtones go theoretically up to infinity. This is low pitch, this is high pitch. And brighter means louder. Finland! I love spectrograms. They're so good. Did it full screen the spectrogram for you? I toggled full screen mode. Did it work properly? Hold on. Here we go. That should work anyway. Oh, it's showing all of my like file locations and stuff. That's actually, I don't think that's good. Okay, cool. I don't think I should censor that, I think. I'll figure it out later. Pretty sure it's alright, but I don't know, can I add blurring and post to a stream? Well, this will work fine, I think. This will work fine. The exporting won't show up, I think. Audacity at least will be. You can do spectrograms on Audacity. new stereo track, and then spectrogram settings, and turn it to a logarithmic. Is there a logarithmic? Scale, logarithmic. There we go. And then here's my music. There we go. It's generating the spectrogram. No, I want a linear scale, maybe? Spectrogram settings, linear. Yes, linear is correct. Yeah, here's the music. And I can actually zoom in on this, I think. Very cool. That's a good idea. I don't actually need a foobar. I can just use Audacity because it has the spectrogram built in. I'm definitely gonna upload this stream or series of streams as a video. That's for sure. Okay, back to the video.
And stresses even high-end CPUs, it would seem like increasing the resolution while maintaining any kind of decent performance isn't possible.
I'll enlist at least
But there are some ways that we can get around this. First, we need to familiarize ourselves with this equation. These are the Euler equations for compressible flow stated in vector form. This is a partial differential equation.
Okay, I think this is the big guy that I have to focus on figuring out how to use. It doesn't look, honestly, it doesn't look terrible. There's no like integrals or anything that I have to worry about. The music is really loud, actually. Okay, there are no like, yeah, whatever. It's all good.
And more specifically, it's a hyperbolic partial differential equation. Both partial differential equations and computational fluid dynamics are complex fields that I spent months researching. So
you spent months researching, I'll do it in a day, I promise.
For those interested in studying more, I left some links in the description to some excellent sources. Performing a fluid simulation is essentially equivalent to solving this partial differential equation. To do this numerically, we need to first discretize our domain. And in this case, we're performing a one-dimensional simulation, so our domain just looks like a line, which represents a single length of tubing. We can subdivide this line into cells, where each cell records its own internal state.
Yep, we're gonna try and learn this stuff together. I don't have any formal education in this stuff yet, but I will. But if I have a head start now with some like actual field experience, how awesome would that be?
We're concerned with three state variables, which are mass, momentum, and energy, which are all conserved quantities. At all times, the sum of these values across the domain must not change. And this makes sense, because we wouldn't expect the total mass of the system to change if there was no mass flowing in or out of the domain.
Summations are easy to make a function
for momentum and energy, which are also conserved quantities. An interesting property of this differential equation, which is extremely useful for optimization, is that the speed of causality in the solution is not infinite. So a disturbance at one end of the domain will not instantly affect the other end. This is not true for things like the heat equation, which predict that heat disturbances will be felt across the entire domain instantaneously. Instead, the disturbances travel at the speed of sound, unless of course the fluid is moving supersonically, but we're not going to deal with this situation very often. That means that if we size the cells in our discretization intelligently, they become completely independent from each other, and this allows you to simulate them in parallel.
Okay, hold on. As I'm listening back to this, I'm realizing that I'm not conveying exactly what I intended in this section of the video. What I mean to say is, each cell will only be affected by its immediate neighbors if the cells are placed correctly and don't violate the CFL, Courant-Friedrichs Louis, I don't know how to pronounce that, Friedrichs-Louis condition. Okay, I need to research what that is. CFL, let me put that in my notes. I'm gonna have like a dictionary of stuff that I want to know. Courant Friedrichs Louis. I spelled Louis like Lewis. Even though I've never seen Louis spelled like Louis.
They become completely independent.
Therefore, it's very easy to split up and parallelize the problem. More importantly, though, the algorithm only depends on the input state of a cell and its immediate neighbors, which makes smaller scale parallelization trivial. Okay, the algorithm... Let's break that down. Establishes the passing of time. Interesting. I will find out more about that. Therefore, is very easy to... More importantly, though, this is the part that I want to break down. The algorithm only depends on the input state of a cell, and its immediate neighbors, which makes smaller scale parallelization trivial. I will figure out what that means on the road, I think. The terrible algorithm that I improvised in the original engine simulator did not have any of these properties, and parallelization of any kind was severely limited. Great, cool. So I need to learn, first of all, how to do multi-threading on Godot. I keep saying Godot because that's how it's spelled, but it's actually pronounced Godot. And then I need to figure out what all of this stuff means.
From each other, and this allows you to simulate them in parallel, which is perfect both for running on the GPU and multi-threading on the CPU.
Running on the GPU. Doing things on the GPU is something that I also need to figure out how to do, I think. But we will cross all those bridges when we get there.
CPUs have special instructions called SIMD instructions, which I talk about in some of my other videos. They allow the CPU to do multiple calculations at the same time on the same thread. Using a CPU to do multiple instructions, which I taught you. CPUs have special instructions called SIMD instructions.
SIMD instructions. Where's my notes? It's in the Godot. So long as each cell doesn't violate the passing of time and are also placed correctly, they will affect each of their fellow cells, thus creating a chain reaction and making it all work. That sounds right. That sounds just about right. That sounds, yeah, that sounds right.
Which I talk about in some of my other videos. They allow the CPU to do multiple calculations at the same time on the same thread.
We're going to be learning a lot about computers too.
Advanced vector extensions, we can run 8 simulations in parallel on the same core.
That sounds good. I'm going to have to research what AVX is and how to do it. Or if it's like, I think it's probably like a library or something.
This is exactly what I've spent the past 2 months working on. This is my fluid simulation library called Tubular, which will power Engine Simulator. It is fully multi-threaded and features AVX support. It can run fairly sophisticated simulations in real time and produces samples fast enough to...
I could just steal his library. However, I want to learn, you know?
Generate real-time audio. The spatial resolution can also be adjusted trivially to reduce CPU load on...
So of course, each cell may or may not need some calculations, so multiple equations could be done, must be done each frame. Yeah. So basically what he's saying there is that especially in order to sample at 41,000 hertz, you're going to want to... No, 410,000 hertz. Oh, let me see. No, it's 41,000. Yeah, let me see on... Let me... where's OBS? Firefox. There we go. Let me remove the foobar thing. Okay, so here's Audacity, right? This is 40... This is the... Look at the rate. This is the sample rate for, hertz means times per second, by the way. Hertz is a unit of what is called inverse seconds, which means repetitions of a thing per second. That means that each sample, let me, waveform. This is a sample. These are samples. There are 41,000 of them per second, and I think they're just stored in a simple what am I trying to say? Up and down. They're stored as Y value, and then X value is per second. Right? That should be all samples are. And there shouldn't be any additional data attached to them. Theoretically. So a wave file would be just the pure, unfiltered, unprocessed data of just every sample in the thing. Or maybe every sample excluding repeat samples. So like if it's just silence, it just marks it as like all samples are at 0. Okay. So what he's saying is we need to do multi-threading because the simulation will be theoretically running at 60-ish frames per second, or even less than that. But if you do multiple calculations at once, you can make it basically go up to 60. I mean, basically go up from 60 to 41,000 hertz.
Cheaper hardware. Let's look at some examples. Each slice represents a cell in the simulation domain, the radius represents the pressure, and the color represents the temperature. We'll start with a stereotypical example of a shock tube. A shock tube is just a tube with two halves which are separated by some sort of barrier or membrane, and the two halves don't interact with each other. The air in the two halves are held at different temperatures and pressures, and then are suddenly allowed to collide with one another, maybe by removing the barrier in the middle. This initial condition is called a Riemann problem, and conditions like this are used in the real world to test CFD algorithms. I was surprised to learn that fluids do not behave intuitively in these conditions and produce a very strange and interesting pattern that you wouldn't really expect. Eventually the two halves will equalize to the same state and things return to normal, and it's a little bit more understandable. We can also use tubular to simulate musical instruments. To understand how this
simulating musical instruments is what I most want out of this project. So what I'm kind of trying to do, I'm making no promises, of course, because this is obviously very complex stuff. But what I'm trying to do is I'm trying to make a fluid simulated text-to-speech program where it's like you like make a human. I'm gonna model a human basically, and I'm gonna model like the parameters that you can adjust, like how large the human is and how much pressure comes out of their lungs, and I'll see if I can make like, and of course the mouth will be the most complex part, where you can like move around the walls and then have the fluids react to the new walls in real time. And then that will end up sounding like a human, making use of like resonance chambers and stuff. And then you sample it with like a little bit of processing, and then it will make a realistic human voice sound. That is obviously like far outside of the scope of even this video. Even Onto the Great has not used soft body physics or whatever, and I have no idea how I'm gonna begin to do this. But that's why we're here. We're learning. I want speech simulated. I want. You know, that's my goal. A bit of a very lofty goal for a new programmer like me. But I'm decently confident. If I stick with it, I'll figure it out. If I can get this first fluid simulation working, then I'll be like halfway there.
To understand standing waves in a pipe. In this demonstration, I have a single length of pipe with a...
Oh, and I do have musical background, so this is actually that's actually going to help me with the physics of this as well. Because I understand a lot about how sound works. Not how pressure and fluids work, but how specifically sound works.
wall on the right side, and on the left we have a pulsating pressure source.
I do have formal education
Notice
in
how
that.
the pressure waves propagate along the tube, then bounce off the wall and return to the origin at the speed of sound. If we tune...
Windpipes are instruments blown by lungs and altered by many things for whatever noise it needs to make, all via the brain sending out info instantly. Exactly. So essentially what I have in my mind is pressure comes directly from your lungs. Pressure comes directly from your lungs, and then it travels up a pipe that we can approximate as a rigid body. And that pipe is of variable length. Not extremely variable, but quite variable. A little bit variable. And it's a variable width as well. And I think we can approximate that as pretty much a direct wave. I don't know though. We'll figure it out. We'll figure it out. And then the complex part is that it passes over the vocal cords, which isn't complex because that's pretty much how open they are. And then from that, it's like a slit where it starts then bouncing around weirder and not just being straight pressure like this tube is showing right here. And then, so we're not only going to have to go with like 2D things, we're going to have to like do like 3D kind of stuff where, yeah, we're going to have to go into 3D for this. I hate that, but okay. I'll figure it out. The mouth is the hard part because it moves around. I think you understand what I'm saying. I just lost my train of thought completely. The things that contribute to the voice are the tongue, the teeth, the lips, the throat, which is the vocal cords, and I don't know. We'll also have to learn about human anatomy, I think. The trachea has a variation of 2 centimeters in diameter in both males and females. That is extremely useful information. Thank you. You are being a huge help. That's actually like extremely useful information. But tonight, what I want to do is I want to try my best to research this stuff and see what needs to be done. Set some high goals. And then, oh, millimeters. That makes a lot more sense, actually. I want to see what needs to be done. And then I want to note down what needs to be done. I need to not just be noting this with my words, although noting it with my words is helpful. Hold on. And then I maybe want to start on the coding a little bit. You have anatomy facts on your side, and I like that. That is very helpful. Basic fluid simulation, cells in a tube. That's what this thing is right here. That needs to be done first. And then what we need to do is take that into 3D. But actually, before we do that, we need to multi-threading / GPU coding. And after we do that, or maybe even before we do that, I think, research WAV file structure / arbitrary audio playback on Godot. Sebastian Log has a log, whatever has a fluid simulation. That's nice to know. I know Anch the Great is open source. This is showing my Godot, right? Yeah, it is. Also, welcome to the stream, Mod Bros. Good to have you here because you know more than I do about coding. Arbitrary audio playback, by the way, what I mean by when I say that is taking arbitrary samples and maybe even before putting them into a file. I know it's not straight up rigid, but maybe we can approximate it to rigid. If not, then I can figure out how to approximate it to a virtual thing. But like, you know, assume spherical cow and all that. Ignore air resistance. Ignore gravity. That kind of stuff. So, by arbitrary audio, I mean like playing audio that isn't in a file. Because I don't want to make it into a file and then play it. I want to play it and then after that make it into a file. Or maybe I can make it into a file and play it. Whatever happens. Oh, by the way, the nose is another factor in human communication. It's another factor I have to take care of. Mod Bros, health. How do I do all of this multi-threading and GPU stuff? Okay, and after taking that into 3D, do 3D cells. I know you don't have like all the answers immediately, but like, it's an open source. It is in Unity, but I can. Isn't GD script like somewhat similar to C#? Because I can probably read it. Okay. I can probably even learn it a little bit while looking at his. I could download Unity. Do I have Unity still? I used to. I don't have Unity still. Maybe I'll get it again for this. But I'm gonna stick with Godot for my main programming software though. GD script isn't too similar, but you can use C# and Godot. You can't just copy paste Unity code though. I thought not. I didn't know you can use C# and Godot. That's interesting. Actually, I did kind of know that because there's documentation on it. And I was looking at the documentation and there's always a C# option. But I can start like learning C#. The trachea connects the bronchi of the lungs to the larynx. The larynx being where the magic is made. That is the vocal cords, indeed. I think the bronchi of the lungs and the diaphragm, that can be approximated as just a source of pressure, an arbitrary source of pressure, or a container that you can choose when to release pressure. Breathing in, you can simulate breathing in. Hold on. You can simulate breathing in by sucking in pressure. By creating negative pressure in the lungs until it fills up properly, and then you can choose when to release the pressure. You know what I mean? GPU coding is something you'd like to experiment with. That's cool, cool, cool. I'm about to experiment with it, apparently. I want also phonetic alphabet to mouth translation. I want to have like some sort of library about... like each phonetic character can translate into a mouth position or a not a position but a specific motion, and then from that you can get the actual text-to-speech thing by stringing together phonetic characters. That I think would be pretty darn cool. And then you could that would make it scalable to every language. you could set it to English and have different phonetic alphabet things mean different things. Or no, it would be different English letters translate, or different English letters and groups of letters translate to phonetic alphabet, which translate to mouth movements. Something like that. We will be researching a lot about biology in around this... At around this step. Research biology. Research linguistics. Research coding. Stinky. I hate working with 3D. Research. Excuse me. Math. Okay. Man, what are we getting ourselves into here? This is a huge project. I'm excited though. I wish I had a taking 5 screen. I kind of need to take 5 right now. Okay, I think if anybody comes to chat, tell them I've taken 5. I'll be right back. Keep listening to your nice music. I don't have a, like, yeah, I don't have a taking 5 screen. Where are you getting all this biology knowledge, Straight Jacket? I'd love to know. It would be very useful. Pharynx, the opening of the larynx, yes, is about 4.4 to 5 centimeters. Or do you mean millimeters, or is it actually centimeters? In length, not varying. Source needed between sex. The larynx itself is made largely of cartilage that then attach to the muscles and such. Very nice, very nice. All right. Let's keep I think for now, let's keep
the pulses just right, they will return to the input in sync with the oscillator, making the wave now appear to be standing still. You may have figured out by now that by varying the length of the tube, it will change how long it takes for the sound signal to travel from one end to the other.
And that's called a resonant frequency.
The resonant frequency of
Heck
the tube. This is exploited in instruments to play notes with different pitches. This effect also works if the end of the tube is open. It might seem counterintuitive that the pressure wave bounces off of nothing, but this is actually what happens in real life. It's a bit hard to understand in one dimension, but in 3 dimensions, you can imagine pressurized air in the tube suddenly meeting an essentially infinite pressure sink in the atmosphere, which causes it to lose pressure rapidly as it expands outward. That sudden pressure drop is a disturbance like any other and produces a wave in the opposite direction towards the left side of the tube.
So does the diaphragm then do pushing motion, or does it only have to do pulling because the pressure in the lungs will... well, it can do pushing, I know that, because you can make your lungs have very, very low pressure, in lower than the outside air. It's like my favorite song. You can like push air out of your lungs even after there's no more air, even after it's at the same atmospheric pressure. But does the diaphragm mostly do pulling, or does it depend on the task at hand? I don't know what I'm saying. Hold on. I mean, does it have any agency in pushing air out of your... Oh wait, because yeah, it does have agency, because you can alter your volume so that you can talk like this quietly, and you're still using the same larynx openness. The larynx aperture is the same. Varies within women and men, however, it's more of a suggestion since, of course, squeaky voice guys and deep voice girls exist. Yeah. So, by the way, speaking of instruments, I was wondering if now that my microphone is unlocked and not being controlled by Windows, can you hear this? You sure can. Very cool. It probably was doing a lot of clipping though. That's an instrument. That's definitely pertains to this current assignment.
A trumpet is essentially
a very good instrument
with one closed end and one open end, acting as a handheld resonator that the player can use to amplify particular frequencies, which we hear as distinct musical notes. To learn a bit more about trumpets, I actually went and bought one just for this video, and here it is. This is my second-hand etude trumpet that I bought online. I have no idea how to play it, and honestly, I can barely even make it make a noise, so I won't be...
Fun fact, I actually do know how to make a trumpet make a noise. I actually know how to make it make several noises, by exploiting the overtone series of my lips, but I don't know how to do it very well. I only had like a week's worth of practice, and I was entirely self-taught, except by my dad a little bit.
Playing it today. The player blows into the mouthpiece, causing their lips to vibrate. The resulting pressure wave...
I know a lot about how instruments work because I was supposed to, because I'm a composer.
Whether air is allowed to continue flowing normally to the rest of the trumpet, or diverted into this additional tubing.
That tubing specifically right there is actually made for tuning. So if you're going to be playing a D, well, it's a trumpet D. It would be a concert. It would be a concert C. But if you're going to be playing a D, transposed D, then you're going to want to extend that tubing a little bit. This right here, you flick that way, and then this whole tube comes out a little bit and lengthens the tube. And then that'll make it just a little bit lower pitch, so it's not out of tune with the rest of the orchestra.
2 and number 1 valves perform a similar function with their own respective sections of tubing. Once the air exits the number 1 casing, it's allowed to flow into the final piece of tubing, which leads to the trumpet bell, and eventually the sound waves propagate into the atmosphere. We can model this in the computer as a series of tubes with 3 valves in the middle. As you can see, the trumpet functions very similarly to the example earlier, and it can be thought of as a variable length pipe. Depressing the valves makes the tube longer with a lower resonant frequency, which we hear as a lower pitch. Handling the interior of the simulation with tubular is fairly easy since it's just built-in components like pipes and junctions. The only part that's a bit exotic is the mouth and lips. A lot of the trumpet's characteristic sound comes from the way that the lips vibrate inside the mouthpiece, and there are entire research papers written.
This will be whenever we get to the larynx part, modeling the larynx, this will be very pertinent. Is that the right word? Of course, we need not worry about extending the cavity of the larynx to the epiglottis. However, the inlet, yes. Everything that's important to speaking, we need to get those in. Everything that isn't important to speaking, throw it out. Because it's going to just sit there collecting dust and doing nothing.
Just about this phenomenon. The lip simulation I'll be showing today is based on the model presented in this paper. Trumpet sound simulation using a 2-dimensional...
Trumpet sound simulation using... Trumpet sound simulation using... Give me a second. Using a 2-dimensional lip vibration model. A 2-dimensional lip vibration model. I hope it's the whole paper. It's the whole paper! Oh, it's important? Cool. We're gonna have to do like so much complicated tubing and stuff. The human voice, we're gonna learn so much about the human voice. Check that out. We got a whole research paper with a bunch of woodwind brass instruments, feedback oscillations. We got a list of acknowledgements, references. We got citations. We got conclusions. We got math in here. Look at all these equations. This is valuable stuff. We hit gold.
Lip vibration model, written by Seiji Adachi.
This one, yeah, this is the same one. This is exactly the same PDF as he shows right here, actually. You can see it's the same font and everything. Except his is a lower quality screenshot.
And Masaaki Sato in 1995. They outline a very simple model where the lips are assumed to be masses held to a fixed point with 2 springs, which makes logical sense. Simulating this is very easy because it's just a typical harmonic oscillator. Since it's 2-dimensional, it captures both the horizontal and vertical movement of the lips. The model also accounts for the forces acting on the lips, like the pressure inside the mouthpiece, the pressure inside the mouth, the elastic and damping forces from the lips themselves, and the Bernoulli pressure acting on the bottom of the lip. All of these pressures are pulled directly from the fluid simulation, so we don't have to model or calculate those separately. In the paper, the trumpet itself is modeled lip by... The model also accounts for the forces acting on the lips, like the pressure inside the mouthpiece, the pressure inside the mouth, the elastic and damping forces from the lips themselves, and the Bernoulli pressure...
Elastic and damping forces is something we're gonna Elastic and damping forces is something we're gonna have to work with a lot with cartilage and stuff. You're right. I think you're right that we are gonna have to pay attention to cartilage a lot. We're not gonna make it entirely rigid because there's gonna be elastic and damping forces. But you can probably simulate that pretty easily by making just a damping parameter. The goal is not necessarily to make this 100% realistic. The goal is to make this realistic sounding, indistinguishable or almost indistinguishable from an actual human voice. Means we're gonna have to simulate turbulence and stuff too. Very interesting stuff. You can forget about adding this protective slime coating since viruses don't exist in the endless void of simulations. Yes, but we might have to take into account the dampening properties of the mucus.
Acting on
I want to try something on a spectrogram real quick. Hold on. I want to try audio setup, recording device, USB microphone. Okay, it's not getting my music. That's great. And change that to spectrogram. Okay, now that's exactly pretty much what I was expecting. So, check out the difference between these two spectrograms right here. This is my voice, and this right here is the instrument, right? What's this? Can I? No, I can't do that. It doesn't work like that. That's sad. Okay, so right here, here's the overtone series of my voice and the overtone series of this instrument. You can see that the overtone series of my voice is actually missing a lot of overtones. One is like it got the fifth in there, the octave, and like it skips a lot. Then there's this, whatever. What's this sound right here? Okay, so this part is where it starts clipping and then it does something weird, which is interesting. You see when it starts clipping the microphone, it gets some more overtones or something. I don't know, but you can see this thing right here. It's gonna have a lot more overtones. By the way, that was slightly flat. It's a slightly flat pitch there. You can see it has a lot more of the overtones. You can see it has a lot more of the overtones because human voice is like more simple or something. I don't know. But hold on. Let's do something even cooler. Generate tone. Sine wave, frequency, I'll go 440. And you can see that the sine wave is just pure. The sine wave is just one overtone. That's true. So, you see the sine wave is just actually like one overtone. That's because each overtone is made of a sine wave, actually. That's why you can simulate any sound by adding... That's why you can do synthesis with a bunch of different sine waves. Just add a bunch of sine waves onto each other. Okay, we're gonna generate a square wave. And you see, it's like all the overtones. These are like two opposite waves. That's loud. Effect. Amplify. You can see how that's like all of the overtones. Isn't that neat? That's also pretty loud. Hold on. And also, listen to that. Did you hear that? If you listen closely, you can still hear the underlying sine wave. You can hear the fundamental tone carrying through if you listen closely. It's less obvious if you start in the square wave, but you can still hear the. Isn't that neat? I love audio. Okay, let's go back to Firefox. I want to turn the music down. And then go back to this.
The lip. All of these pressures are pulled directly from the fluid simulation, so we don't have to model or calculate those separately. In the paper, the trumpet itself is modeled using a convolution filter with a measured impulse response of a real trumpet. According to Reddit experts who criticized me for doing this exact same thing with the original engine simulator, this is not a real simulation, so we're going to be replacing this filter-based approximation with an entire CFD model of a trumpet using Engine Simulator's fluid simulation. Visualizing the trumpet using this simplified interface can be useful, but it's not the most exciting.
That's less of a that part of the video right there was less of an educational thing that we need to focus on and more of like a critique of Redditors telling him he's wrong, which is pretty cool. But I don't know, the coffee is worn off. I don't know, I don't understand what we're talking about. But yeah, we need to pay attention to that less. I want to do the tubular model. I want to, yeah.
Considering that I spent many weeks studying fluid simulations and staring at math all day, I decided to spend a few days doing something completely different by making a 3D trumpet model in Blender. I like to do this from time to time. I don't really like working on the same project for too long, and I don't really like working in the same field for too long. So sometimes I'll switch over from programming and do more of an artistic project. In this case, it was actually relevant because I can use it in my game engine to actually show the trumpet and kind of demonstrate the way the Engine Simulator's fluid simulation is going to work. So it was not a complete waste of time.
I'm not going to be building a separate game engine
There are
to do
some
this.
smaller details that I just didn't really bother modeling because they're not necessary. But this is good enough for my purposes, and this was rendered using my ray tracer, which I showed in one of my older videos. With that completed, it was time to work on the 3D Fluid Visualizer, which is going to be used both in Trumpet Simulator and Engine Simulator. The fluid visualization is
throat singing is definitely something we want to add
of Engine Simulator, so I put quite a lot of thought into what it should do and how it should work. The visualization that I showed previously in this video seems okay at first glance, but the problem
throat singing is something I want to learn how to do, honestly.
Velocity very well. And this is very important when you're studying engines. In fact, it's essentially impossible to see the motion of the fluid unless there are sharp temperature or pressure fluctuations being pushed across the domain. My original plan was to implement a particle-based system very similar to what I implemented in one of my older videos.
Now he's getting a little bit more specific and saying like
a few months ago by adding
how his fluid simulation works,
engine, which allows for the rendering of some very high polygon 3D particle systems.
It's just a little bit less useful for us.
Reasons. The main reason is that it's very easy
but it's still
to
interesting.
Fluid velocity in this way. I think it's a lot easier, especially for a casual audience. Instead of showing, like, for example, a vector field or just arrows pointing in the direction of velocity,
I think I'm going to go with a vector field.
And it's not really very intuitive to look at. This point is less important for engineering and scientific applications, but since
I'm counting this, I'm counting this as an engineering / scientific thing. Honestly,
targeting a more general audience, presenting the results in a
the opposite of imposter syndrome
is a lot more important. The implementation of the visualization is fairly straightforward. It's basically a collection of particles released into the fluid system, and they can be moved around by the airflow inside. Interestingly, the visualization itself is a simple physical simulation of point masses in a fluid. So we're using a simulation to interpret the results of another simulation. These particles can either be spawned in randomly or injected at a certain point, like smoke in a wind tunnel. The particles also change color depending on temperature, and they also change scale depending on pressure. To clearly show pressure and temperature, I also added
that
more standard pressure and temperature display that we discussed earlier, and it follows the length of the tube. For PCs that make...
If you're looking at the lyrics with the opening of pharynx facing away from you, the two folds / false vocal cords are right above the actual vocal cords, which you already know. I think I might know what you're talking about. I might know what vocal cord diagram. Vocal cords. True vocal folds, false vocal folds. Somewhere. Doesn't really show it here. False vocal cords. That's a good one. Hyoid bone, thyroidoid membrane. False vocal cords. These aren't exactly made of slime, I wouldn't say. And these are the true vocal cords. These are the muscular ones. And these ones are not muscular, but they're not made of mucus. They're made of like slabs of skin, basically, that only move based on air pressure. And then these are the true vocal cords that are muscle actuated. This is the trachea. This is probably where our simulation is going to end. Like, this will be simulated as a basic container that holds pressure, and then that can be released at any strength you want. It'll pass through these, which will be muscle actuated. These will be manipulated by the pressure. And then, oh, this is going to be a complex system, isn't it? And then from there, it'll travel up here. And then it will travel through these things, splitting the thing and making sounds based on the, you know, everything right here. This will be the real complicated part, honestly. This is the part where you're gonna have to do like all sorts of rigging and stuff.
Maybe don't have a lot of GPU capacity, displaying tens of thousands of particles at a time might be a little bit excessive, so I do have some
I'm gonna go with
backup
vector fields, like I
visualization
said.
schemes that the user can choose from, or they can just turn them off completely. Before I show you what this sounds like, there are a few things that I want you to keep in mind. First of all, some very important elements of the simulation are not yet in place. Right now, it's assumed that the trumpet has a completely cylindrical bore with no cross-sectional variation, which is obviously not correct. The simulation does support variable cross-sections, so it is possible to model the trumpet's flare.
I don't like here how he didn't explain how it supports the different cross-sectional areas, because different cross-sectional areas is exactly what I want to know. That's like pretty much the whole thing that I need to know to make the mouth. It needs a lot of different cross-sectional areas.
And the bell, and I have been able to successfully simulate things like two-stroke expansion chambers, but the implementation isn't really complete yet, and it wasn't ready for this video. Without taking the trumpet bell and flare into consideration, the trumpet's intonation is seriously messed up, and you can't really play music on it. Another thing to note is that the lip model has many parameters to control, as does the rest of the trumpet. So playing this thing is not as simple as plugging in a MIDI keyboard and then playing random notes.
It's pronounced
Just like
MIDI.
a real trumpet, you have to adjust the blowing pressure, your lip geometry, the lip stiffness, and the trumpet valves themselves, and doing this effectively on a keyboard is not that easy. So the most I can play for you guys right now is a simple chromatic scale and just a few random notes to show how the trumpet handles transient effects. We're mainly interested in the general character of the sound anyway, just to validate the fluid model.
In order to get this higher pitch sound, he must have adjusted the lip parameters and then the, you know, the blowing pressure.
The most amusing part of this simulation for me is the fact that it just sounds like a computer that is really bad at playing the trumpet, as opposed to the usual problem of computers sounding extremely robotic and synthetic.
Yeah, so basically, like this comment down here says, professional tutor player here, former. You warned us about the intonation and difficulty of tuning in the lip inserted parameters in real time. Then the sound of simulation started. It sounded exactly like somebody struggling to get a good tone for a weirdly built, aka no cross-sectional area, trumpet. This is impressive, and I agree. Listening to that sound, so amazing. Yep. Okay, it is very impressive. I thought I saw a comment somewhere about, like... Fluid simulation is one part of it. Or amplification. Sympathetic resonance. Sympathetic resonance. Oh. I thought I saw a comment saying some useful information. The rest of the lyrics, you mean the same slime that lines the rest of the lyrics. I see. I thought I saw a comment that said something useful and I forgot what it was now. Yeah, I forgot.
There are still some very obvious
We also need to add the yeah. It does add to the deepening of the voice, yes.
issues, which I...
Oh, and you can actually vary the position of that too, so that's something that we need to consider.
I haven't really solved yet. For some reason, the computer has to blow way too hard into the trumpet to actually make a decent sound. I don't know how to play the trumpet myself, but my understanding is you shouldn't actually need to blow such a massive quantity of air into the instrument, but for some reason, just the model works better when you do that. Obviously, the multitude of parameters need a bit more tuning before this thing is ready for the stage, but it is cool to see how the parameters affect the character of the sound. Here are a few demonstrations. So first we can just try blowing way too hard into the trumpet and see what happens.
Oops. Yeah, I don't have YouTube Premium, sorry. Okay, I think now it's a good time to move on to this video right here.
I want to simulate fluids. There are two main approaches, using particles which
because this I think will help me, the just plain old straight up fluid simulation, that'll help me with the project I'm currently working on right now. The beginning step of this thing. Hold on, let me see. The beginning step, which is basic fluid simulation. Cells and tube, or whatever. Which is Eulerian fluid simulation, as this guy puts it.
Lagrangian, or using fixed cells, which is called Eulerian.
Eulerian. Eulerian is the one I'm going with.
In this video, I want to focus on the fixed cell Eulerian approach. The particle approach is fun though, and in Unity is easy to do. I just create a tiny sphere with bounciness 0 and friction 0, and spawn a few thousand of them. I might experiment with particles in a future journey. It's also possible to have a hybrid where particles morph into cells that morph into particles, but I will leave that for future experimentation. There are so many places I want to go that I can't, like inside the Earth, through the Sun, see black holes colliding. I can't do these things in reality, but maybe we can simulate them. In the Eulerian approach, the fluid is represented by stationary cells. Each cell has a single vector which represents the velocity of the fluid in that cell. Let's add some coloured ink to the fluid. The ink flows in the direction of the velocity. This is called advection. I'll talk about how we can implement advection a bit later. To simulate places I cannot go, I feel a useful first step is, can I simulate a simple fluid? No viscosity, no air, and I'm going to keep to 2 dimensions. So that's my goal.
Oh, it sounded like the ad was the sound the trumpet made. Nice.
For this video, and I'm going to use GPU shaders because shaders are fun. Let's make the color sources persistent, and then I'll add a drop of each color. Let's increase the resolution to 30p and turn off the arrows. I started this journey by watching some videos by Matthias Müller, who is physics research leader at NVIDIA. I read through Joss Stam's Real-Time Fluid Dynamics for Games. I feel that Brian Trevathan's thesis, Physically Based Simulation for Computer Graphics, gives an excellent survey of fluid simulation techniques. I couldn't understand his maths at first, so I spent several weeks watching videos on maths by Comitant, Elucider and Dr. Payam.
In French, la place means the place. So you know you're in the right place.
It feels a little static, so let's add some noise to the color. This gives a little sensation of movement. We can actually increase the resolution more to 480p.
Alright. We don't necessarily need to add, by the way, Straight Jacket, we don't necessarily need to necessarily simulate all of these muscles. We can just like simulate their effects as well. We can say, like, given these parameters... This is a really quiet song. We're back to dreamscaping. What's next? Nice. I think the station, the playlist just looped it on itself. Okay, so we don't necessarily need to simulate all of these things. We can just say, like, given these parameters will change, you know? But it's definitely very nice that you are researching all of this. It's very helpful. I'm gonna definitely use chat as like a kind of note resource thing.
This is pretty fun, but if I go back down to resolution 8p and turn the arrows back on, we can see that whilst the fluid is technically moving because we have velocity arrows, but the arrows themselves are not moving. The fluid movement is not moving itself. And look, I can drag these arrows so they're all pointing to the same
Honestly,
cell.
I'm gonna just turn off the music for now.
So that means we've got fluid flowing into this cell and no fluid flowing out. So the fluid is either being destroyed, or it's being infinitely
I
compressed
understand.
like a black hole. But generally, it's not behaving like a typical fluid. There are two things that we need to make the simplest fluid simulation that I'm aiming for in this video. One of these things is conservation of mass, incompressibility. When fluid enters a cell faster than it leaves, this is called negative divergence. And when fluid leaves a cell faster than it enters, this is called positive divergence. So here we have white fountains that represent matter being created, and black whirlpools represent matter being destroyed. Now, to make our simulation, we need to clear this divergence. Joss Stam used some fancy maths for this using Helmholtz decomposition, but the maths was hard for me to understand, and calculating the curl-free field needs an iterative approach. Matthias Müller proposes an approach that does still need iteration, but I find much easier to understand. We do need to change representation slightly though. Instead of storing the velocity at the center of each cell, we're going to store the velocity at the edge of each cell. It's a little less intuitive to look at, but calculating divergence is now really easy. All we have to do is add up the velocities flowing out of the cell and subtract the velocities flowing in, and that's our divergence. In my shader code, I take the velocity flowing out of the right hand side, add the velocity flowing out the top, and subtract the velocity flowing into the left hand side and into the bottom. And
I'm liking this video a lot. It's like very specific and exactly what I want. But the problem is that it's making my head hurt a ton. I think I'm gonna need to take a break soon so that I can just like close my eyes for a second, and then I can come back with like a fresh mind on this, and we can start actually working on this stuff. Actually, you know what? Maybe we should just follow this like a tutorial. Maybe we should actually get into the actual coding of it now. So we're gonna want cells that store their velocity, and then somehow that moves colors. Let's follow this step by step.
The place, so you know you're in the right place.
You are in the right place. Okay, so the cells have their velocity as a vector, right? And then I'm going to make a grid of 2D cells that have their velocity as a vector. I'm going to just use the Godot's built-in tile map. And then a second. And I'm gonna find out how color math in Godot works. So okay, let's make our let's make our first thing. We're gonna make a child node, tile map layer, and this can be named tiles 1. And then these tiles can have they're gonna have a script on them, of course. Tiles 1. Let's make a new folder. Let's not make a new folder. Okay. And okay, hold on. Let me make a white square in GIMP real quick. The larynx has got muscles intrinsic entirely The larynx has got muscles, intrinsic entirely inside the larynx, and extrinsic without their origin elsewhere, and affect the larynx, with intrinsics working on phoneticking and breathing. Nice. I think we're mostly gonna want. I'm gonna adjust my mic. It might cut out. It did not cut out. That's good. Time for water. Okay, so I'm gonna make a white square in GIMP real quick. I'm gonna make it 1 by 1, honestly. And then I'm gonna export it to cell.png in the fluid sim. Give me a second. What did I name the project? Fluid sim. Simple. And then we can like modulate. We close Audacity, I don't need it. Okay, so now we have cell.png. And tile map layer has no tile set resource. One new tile set, add atlas cell. 1 by 1. Now let's see tile map. I don't think it likes 1 by 1 cells. Extrinsic modules elevate, depress, and constrict the larynx, but that is, yeah. I don't think it likes having 1 by 1 cells. If that's the case, I can turn it to like 8 by 8 or something. Tile map. One by 1. Let's go 8 by 8. I know 8 by 8 works. Even though it's going to take technically, I guess, more data. It's going to be the same color anyway, isn't it? I'm going to also upload it to cell.png. And then just replace it. Okay, cell.png is bigger now. Yes. Map. That is a good idea, thank you. Okay, maybe I'll make 2 cells. 8 by 16. And then one of them will be transparent. And I'll name this one cells plural. Okay, now I can paint them. Okay, good. Now I need to make some logic for them. Now that we have basic cells, let me put on the music again. Now that we're not watching a video. Okay, 1, 2, 3, 6 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'll make it 12 by 12. 7, 8, 9, 10, 11, 12. That's 12 by 12, isn't it? Actually, let me make it 12 by 12 with origin at 0, 0. And I want to make it do the proper y values. No, I'll do negative y. Drawing rectangle. I'll do 16 by 16. There we go. Rectangle 16 by 16. Hide the grid, please. And now we have a grid of cells. rid of tiles. Output is paint tiles, okay. Must be greater than 0 pixels. Image is empty. Interesting. Well, I fixed that already, so yeah. Okay, hold on. Now we're gonna need to add custom data layers to this. Physics layers, terrain sets, navigation layers, nope. Can we modulate colors on specific tiles? Is that a thing we can do? I'm gonna make a vector 2 velocity. I think custom data can be edited per tile. I do have to paint it on though. Paint, velocity, yeah. 0, 0. And it will be a vector 2i. Oh, my neck. Okay, hold on. You know what I'm gonna do? I'm gonna take 5. I'm gonna give me a second. Making something. All right, hold on. Let me window capture. Yep. 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 Screen. Oh, not flip. Reset. Form. Fit to screen. I need a break because my head hurts. Like, actually, I'm getting a headache from all of this learning. Genuinely getting a migraine. Okay, I'm gonna just like lay down for a second and turn off the lights. Alright. I'm back. 5 has been taken. So I got some Tylenol, made some tea, cinnamon apple spice. Very nice, very nice. And now we're going to do some vector math. How do you like that, Obama? I'm gonna start. I turned off the lights. I am gonna keep them off because I like the darkness better while I have a headache. When I get a headache, you know I'm doing some really good learning. I think I'm gonna try to be a little bit quieter, take things a little bit easier. Do a real good late night stream, you know? A real good, nice late night coding stream. The tea is not ready yet. Set a time. You can still hear me if I'm using my quiet voice. 8 minutes. What a perfect song. Let me turn this all the way up. All right. Very much cozy internet. Cozy coding. That should be the name of this series, cozy coding. We're gonna figure out how to make vectors. I'm like the Bob Ross of coding. Tiles1.gd is what I'm looking for. I'm so tempted to drink this tea before it's done though. I need to make an even cozier playlist. Ready? Dude, I don't know. I don't like how the cursor stops showing up. So basically all tiles have new value associated. And we're going to want to be able to edit that per tile. We are going to code a happy little vector. Only one tin can. Canvas layers can be used to read. Unlike canvas dot modulate, right? Sprite's color. Modulate and self-modulate. Color is a vector 3, right? Okay. I forgot how to do input events. Okay, yeah, that's how it works. Okay, hold on. Project settings. Yep, you probably can't see this. Input map. Click. Actually, just press click. It's going to get mouse key. Mouse position. Take a look at this position. Get mouse local E pose. And what this is going to do is it's going to take the tile map, pose dot to local. Is that right? Let me see. Vector mean? What does vector mean? Yeah, I'll tell you that in 1 second. Let me I forgot how to do this. I remembered how to do this a while ago. There is no functional, non-existent function to local in basic vector 2. Oh yeah. What? I don't actually know what that means. Okay, so a vector basically is a line that has a position and what is it? Direction and magnitude. You know, vector. Oh yeah, that guy. It has direction and magnitude. So direction means which direction it is pointing, of course, and magnitude means how long the line is, or how, yeah. So velocity can be velocity in a 2D space, for example, can be expressed as a vector 2, because velocity in a 2D space can be expressed as a vector 2. Say you're here and you're moving here, then the vector 2 would be this line. The vector 2 would be this line. And that's loud. The vector 2 would be the line that, the vector 2 would be the line that connects the two positions. So it's, the reason it's 2 is because the x value is the distance from this column to the column where you want to be. And the y value would be the distance between the row and the row you want to be. Let me see if I can... I have an idea. Okay, here we are in a program. Oops. This line is a vector. And this line is the x component of the vector. Notice how it lines up here. And then this line, and then this line right here is the y component of the vector. Notice how it lines up right here. So this would be, it starts from half and goes to half. So this would be 3. The measurement of, so this could be expressed as, this thing can be expressed as a vector 2. He is done. That's very nice to know. I was waiting to drink that. So this is a vector 2, and this is the vector we are getting that is described by this value right here. So this vector is, in Godot, this would be negative towards negative y, and this is x. It goes from half to full, so 1, 2, 3, 4, 5, and a half. So this line is vector 2, 5.5, negative 3. And vector 2 can be used for a lot of different things. It can be used for finding, like, you know, moving. And you can do cool things with that. For example, you can normalize it. Dot nor, which I'm not exactly sure what it does, but I think what it does is it sets this to be equal to 1. So this would be this, yeah. These two vectors are going to end up being the same length, and this one is going to be between them, so to where it makes, you see this circular shape. It isn't exactly, but it would be a circular shape, and it would preserve the angle. So yeah, that's what a vector is. I also want, over here, camera 2D. so that you can, give me a second. See how I'm going negative Y and the camera moving up? That's Godot for you. Normalize the sets of magnitudes to 1. The set's magnitude to 1 without changing direction. That's what I thought it was. Now watch this. Now I have a camera and we can actually see this thing. But of course we still have an error because I forgot how to actually forgot how to get local positions. Sorry about my drinking sounds. Local dot Godot. I forgot that I haven't showed you the. Oops. Actually, this work. This is not working. Wait a second. Just a second. Well, that really didn't work. That's actually really weird. I don't know how to make that work. Okay. You know what? That's okay. I like this song. Let me look up how to make the global position work. Local. File map. We want to do methods. Set cell, no. Local to map. Map to local. That's what we want. Local to map. That isn't exactly what. Hold on. Let's see what this number is. Okay, well. It's actually doing exactly what I wanted it to immediately. That's actually... That's actually exactly what I wanted that function to do, and I didn't even have to fuss about it. I'm so good at coding, guys. I think I'm gonna go on for 30 more minutes until 11 EST, and I'm gonna get off. I do have to stream Noita in the morning, which will also take up brain power. Okay. So I want to get the tile, and for that tile, okay, hold on. Well, I can. 12:30. Not that you're not that far off. Just 2 hours ahead. Where who tile equals the return value of this function. So now if I print clicked tile, it will print tile position. So now what did I want to do? Oh yes, I wanted to modulate the map to local. Map to local returns the centered position of a cell in the tile maps. So is there a way? Jack, I think you would know this. Is there a way to modulate the color of each of these tiles separately? Color. Yeah, okay, yeah, there actually is. I found it in the methods. Oh, you guys weren't looking at Godot the whole time. Oops. Get layer modulate. Returns. How map layers mod? Is there one that I can do single tile? Tile data. Update internals. Okay, hold on. Tiles 1. Self-modulate will be the one I want. I think that's the one I want. Well, now we know which the clicked tile is, and we can feel free to edit the velocity data all we want. We can feel free to edit the velocity data all we want now, but I still don't know how to edit the color data. The reason I made a tile map with only one type of cell was because I wanted to make the cell arbitrarily color itself to whatever color I felt like, so that we could do things like mix colors of fluid stuff. So let's see. Can we do... see if somebody else modulating single tiles. Of course, somebody else knew, or somebody else. Per tile modulate property. This is exactly what I need. Reddit always has the answers. Modulate sells dictionary. I want to use tile data run. Okay, so I don't need all this. I'm gonna copy this code and see, doing the thing and see how it works, basically. I don't need all this. You need this. I need this to be up here. This. This, and this should be in the ready function. Use tile data runtime. Don't need the layer because that's a different. I showed my flare. Nice. And I mean, oh, I forgot to go back to Godot. Oh, sorry about that. We don't need a layer. That should all work. Now what did that do? Nothing. Okay, hold on. If I think that's because they're all outside of the. What if I do that, right? And then I check that out. One of the tiles is a different color. Let me move out the camera. Actually, let me. You see that? One of the tiles was a different color. That's exactly what I wanted. Are we gonna spend the whole night just trying to color tiles instead of actually making a fluid simulation? I want the scale to be there. Oh, this. Oh. Let's see. Check that out, 3 colored tiles. Isn't that neat? 3 colorful looking tiles. Wow, this is actually like. Here we go. It actually. Oh, you can't actually see the 3 colored tiles because. you actually can't see the colored tiles because it's not actually showing up on the thing. Whoops. Yeah, I assure you there are 3 colored tiles in the place that they were supposed to be. Modulated Cells Dictionary. Okay, so this is basically a dictionary of all it's basically a dictionary of all the cells that have changes in color. So basically in the modulated cells, the position of vector 2i tin tin, that would be the color that equals the color red. And in the modulated cells dictionary, the position of that dictionary color 1515, that's green. And then so this returns this returns the if the cell has coordinates in this dictionary, it'll return true, I think. And then title.runtime update should theoretically then color it. Tile data modulated cells that get chords. Color white. I don't know what that means. They're white unless they're not, I guess. Okay, so the tile data.modulate. The tile data.modulate. Okay, so it's a modulate of vector 2 modulate apparently. I can't understand this line of code. Basically, it's working though. I just need to make it turn a color whenever it's clicked. Okay, hold on. Okay. I do not have a cat, no. Wait, where did you get that idea? Okay, that didn't work. Why didn't it? Where, oh, I don't think you had an idea that I had a cat. I think... Where'd you find all that stuff? Dang, you're good at this. I do have a website, yeah. I composed. Yeah, did you find my Instagram? How did you find my... My family has a cat. several. Did you find my Instagram? That's so funny. Oh, I see. I showed my user Flare, so you were able to find Liam Jones Composer on the internet. I see. And therefore you found my Instagram website. Interesting. That stuff I'm not going to be able to hide because I'm going to keep Liam Jones Composer forever. It's not necessarily that sensitive information either. I posted one of my shorts on Instagram in hopes that somebody would come to the live stream from there, but like nobody viewed it on Instagram. I'm gonna probably post more on my Instagram about what I'm doing on YouTube and turn it into a little bit less of a personal account, I guess. As for my website, I can definitely do something cool with that. Just like, you know, not now. Okay. So I'm adding to the dictionary, am I not? Yeah. Oh yeah, of course, still on about that. If I was a scammer, I think you'd probably be able to figure it out by now. If I was a scammer, I'd be a pretty terrible one. It's adding to the dictionary. Oh. I think I heard about that guy. Isn't he like a religious composer? He composes for like churches or something? I really can't hide my extremely sloppy internet history, I think. At this point, there's no going back. Can't find my new Reddit? Interesting. You can see Godot, right? Yeah, you can see Godot. In that case, I can go look at my profile and see why that might be. It's probably because it's such a small account. It is what it is. I have 9 post karma and 7 credit karma. 7 comment karma. don't think there's any specific security settings on it. Okay, so I need to call tiledata.modulate. That's right, is tile data. I call tile data. Yeah. Oh, okay. Maybe. Yes, I closed it. Okay. Tile data. Well, I really don't know how to do this. Excel tile data. Okay, maybe. Well. See you later, straitjacket. Something happened. That's for sure. It turned, well, you couldn't see that, so it turned the entire thing blue. And I think that's gonna be good enough for me. I'm gonna call it a night too, because it is almost 11. It is 10 o'clock, in fact. And I'm now the only one in stream. Yeah, I had a good run. I think this was a great first stream, honestly. I will see